In this lesson, we're going to take a look at examples of when limits do not exist. And this is important because it will help us to better understand limits, and it will also help us to better understand derivatives of functions and when they do not exist. Because the limit definition is used in the derivation of the derivative of functions. So what we're going to do is we're going to look at several examples here of different cases when limits do not exist. The first one we're going to look at is what's called a break discontinuity. So consider this function. We have a piecewise defined function here. F of x equals x squared plus 2 for x larger than 1, and 2x for x less than 1. And here's what the graph of that function looks like. This piece right here is the x squared plus 2 part, and the piece down here, that part right there, that's the 2x part. And right here at 1 is where you have the break. Now let's see what happens when we try to evaluate the limit as x approaches 1 of this function. So we're going to look at and we want to see why this is actually not going to exist. So what we're going to do is we're going to take x values here, and we're going to let them approach 1 from the left and from the right, and we're going to see what happens to the function values. What are they doing? So as we do that, keep an eye on what happens to the function values over here. They're right there on the y-axis as we let x approach 1 from the left and from the right. So let's do that. So we see that as x is approaching 1 from the left, let's step that in a little more slowly. All right, as x is approaching 1 from the left, it looks like the value on the y-axis is approaching 2. Right now x is 0.99, f is 1.98, 1.99. It looks like it is getting closer and closer to 2 as x approaches 1 from the left. So let's write that like this. So as x approaches 1, and we're going to indicate from the left like this. This is common notation. That means x is approaching 1 from the left. F of x is approaching 2. So this notation means x is approaching 1 from the left side, that superscript minus. Now let's see what happens as x approaches 1 from the right side. So let's move over here. So now we'll step x in towards 1 and keep an eye on the values on the y-axis. It looks like they are getting closer and closer to the number 3. Alright, yeah, it looks like they're getting closer over here. They're getting very close to the number 3. And so as x approaches 1 from the right side, and that's how we'll indicate this 1 with a little plus, that means x is getting close to 1 from the right side, or from the larger side. So as x is doing this, f of x is approaching the number 3. Well, now the problem here is that for a limit to exist, remember in our definition, for our limit to exist and equal the number L, the f of x has to be approaching the single number L no matter how x is getting closer and closer to c. L has to be a single number. Here we have two different numbers, and they're not equal to each other, of course. These two numbers are not equal, of course. So we're left saying that this limit just does not exist. F of x is not approaching a single number L. It's approaching two different numbers depending on how x approaches 1. So this limit does not exist. So that's an example of a break discontinuity. Now let's take a look at this function. So here we have an example of what we call a vertical asymptote. Now we're going to study vertical asymptotes in more detail later, but this is just a brief example of another situation in which a limit does not exist. So let's take a look at the function f of x equals x plus 1 divided by x minus 2. So that's the function we're going to consider. And let's show that the limit as x approaches 2 of f of x does not exist. So here we have a table, and we have x values approaching 2 from the left and from the right. And notice what the function values are doing. As x approaches 2 from the left side, these function values are getting infinitely large in the negative sense. And as x approaches 2 from the right side, the function values are getting infinitely large in a positive sense. So we see that the function values in one direction, as x approaches 2 from the left, f of x is approaching negative infinity, it looks like. And as x approaches 2 from the right, our function values are approaching positive infinity. Well, obviously, infinity is not a number to begin with, and it's approaching two different types of infinity, so this is a very bad type of does not exist. And we can see that from the graph down here. If we look down here at this graph, here's what our function looks like. You see the function right here is 2 on the x-axis. The function breaks upward towards positive infinity as x approaches 2 from the right, and then it breaks down towards negative infinity as x approaches 2 from the left. The dotted line right here just indicates a vertical asymptote. It's not actually part of the graph. Only the blue, the solid blue curve here, is the graph of the function. And notice what happens as we let these x values approach 2 from the right. You'll see that the function values are going to go up to positive infinity. And then as we let x approach 2 from the left, we'll see that our function values are going to go down to negative infinity. So let's see that. So you see those function values are starting to get larger and larger. Just step that in slowly. So there, x is approaching 2 from the right, and our function values have just gone off screen. They're getting infinitely large. And the same thing from the other side, but they go down towards negative infinity. And there we go. Alright, just went off screen. So in this case then, we are left stating that the full limit just does not exist. So we would just state so this limit does not exist. Now let's take note of something important down here in regard to this limit not existing. Note that if we look at the limit of the numerator, the x plus 1 part, as x approaches 2, that is the number 3. So you see the top is approaching the number 3. This is approaching 3. And as x approaches 2, the denominator is approaching 0. So when we look at the limit of the numerator divided by the limit of the denominator, we get this 3 divided by 0. When that occurs, when you have a non-zero number divided by 0, that immediately tells you that your limit is not going to exist. So anytime you see a number like 3 over 0, or any non-zero number divided by 0, when you look at the limit of the numerator over the limit of the denominator, that immediately tells you your limit is not going to exist. Now, in a previous problem, in a previous video, we saw that we had forms like 0 divided by 0. Now, when you have this, well, that means your limit might exist, and you have to analyze it in a little more detail. So we have to keep these two cases in mind when we're looking at limits. Now let's take a look at this. So here we have a general rule that we can follow. When we're looking at the quotient of two functions, this is what I was just mentioning. When you're attempting to evaluate the limit as x approaches c of f divided by g, you have three cases that may occur. If you look at the limit of the numerator over the limit of the denominator, and you get something like m divided by n, where the bottom is non-zero, then your full limit is going to simply be m divided by n. That's actually a result that we'll restate later along with some other properties of limits. On the other hand, if you take the limit of the numerator divided by the limit of the denominator, and you end up with a number m divided by 0, where m is non-zero, then your limit is not going to exist. There is no hope for it. It's going to DNE. Now later on we'll specify a type of DNE in this case. It could be a positive infinity or a negative infinity type of DNE, so we'll look at that soon in another video. But for right now we can just say it does not exist in this case. On the other hand, if you take the limit of the numerator over the denominator and you end up with 0 divided by 0, well then the limit may or may not exist. You really don't know what it's doing. You're going to have to analyze it in more detail, and there are techniques that we will develop later on to help us out in that. Techniques like the cancellation technique and the rationalization technique, where we do a little bit of algebraic manipulation of f over g, and then we'll be able to evaluate the limit. So that'll be in another video as well. So we have these three general rules that we can follow. All right. Now let's take a look at this example. So we're given the function x plus 1 divided by x squared. Let's show that the limit as x approaches 0 of f of x does not exist. Well, using the rule that we just saw, if we look at the limit of the numerator over the limit of the denominator, we see that we get 1 divided by 0. Notice that when we're looking at limit as x approaches 0 of x plus 1, let's note that that is 1, right? As x is getting closer and closer to 0, it should make sense that x plus 1 is going to be getting closer and closer to the number 1. You can just plug 0 in for x in this case. This is a polynomial, and we will see a rule later on that will justify that we can just plug the c value into the x values for any polynomial in here. And it should be easy to see anyway right now that this limit is 1. And of course, the limit of the denominator, of course that's going to be 0 as well. If we just plug 0 in for this x, we get 0 squared. And we will have a rule that will clarify that later on, but it should be easy to see right now that if you take a small number that's very close to 0 and you square it, you're going to get another very, very small number, an even smaller number. Remember, a small number squared is going to be an even smaller number. So it should make sense that this is 0, and you can just plug 0 in because this is a polynomial. And like I said, we'll have a rule later on that states that you're justified in doing that. But for right now, it should be easy to see that these two results hold without us having to create a special table for that to justify that. So by the previous result, then, this limit does not exist. You can also see that it does not exist from a graph. Here we have a graph down here. Notice that if I were to pick x values and then look at the corresponding function values on the y-axis, if we let x approach 0 from the right and then from the left, notice how the function breaks upward towards positive infinity. So these values will be going up to positive infinity as x approaches 0 from the right. And the same thing as x approaches 0 from the left. The function breaks upward, so the values here on the y-axis are going to be breaking upward to positive infinity as well. And you could also create a table if that still doesn't convince you. You could create a table down here. Here are small x values that are getting close to 0 from the left and from the right, and here are the corresponding function values. and you see that these function values 20, 90, 9,000, 9,999, they're getting really, really large. They're going to infinity from both sides. So you see this is approaching infinity, and this one side is also approaching infinity. And for now we're going to say infinity is a DNE. Infinity is just a special type of DNE. Later on we'll see that we may state that this limit is infinity. That's just a special type of DNE. But for right now, DNE is just fine. We'll get to that later. All right. The last example we're going to look at here for a limit not existing is what we call infinite oscillating behavior. Now this is a rather strange example of when a limit does not exist, and you won't run across it very often, but it is something that we need to consider. So let's take a look at the limit as x approaches 0 of the sine of 1 over x. Now down here we have the graph of what the sine of 1 over x looks like. So you'll notice that what we have near the origin here is we have an infinite number of oscillations of the sine function all being smashed together near the origin. Now we're going to let x approach 0, and we're going to try to see what the sine of 1 over x is doing. So in this graphic over here, that's what we're going to do. So let's move x back here. Now what we're going to do is we're going to let the x values here, that dot right there, approach 0 from the right, and keep an eye on what happens to these function values. Let's see if they're approaching some limiting value L that we could state that this limit is equal to. So watch what happens to the function values as x approaches 0. Let me step it in a little more slowly now. The function values are just jumping all over the place. Because there are an infinite number of oscillations around the origin, the function values never settle down to a particular number. They just keep jumping all over the place. And the same thing if we let x approach 0 from the left side, the function values still keep jumping all over the place. You see that they're never approaching a single number as x approaches 0. So because of that, we're left stating that the limit as x approaches 0 of sine of 1 over x does not exist. Now let's try to understand a little bit why do we have the infinite number of oscillations in here for this sine of 1 over x function. What is why is that occurring? Well, let's consider this graph. So right here we have the graph of just the regular sine function. That's y equals the sine of x. Okay, this is our standard sine function right here. Now if we want to consider what is the sine of 1 over x doing, well, notice this. As x approaches 0 from the right, so x is getting very close to 0, but it's a positive number. 1 over x is approaching positive infinity. It is getting infinitely large. Just try that on your calculator. Look at 1 divided by a very small positive number like 0.00001. That's going to be a very large positive number. So you see what's happening is in the this piece right here, as we let x approach 0, this piece is approaching positive infinity. So it's as if you're taking all of these oscillations, all of the oscillations out here, and smashing them down around the origin. That's exactly what's happening. And the same thing on the other side. As x approaches 0 from the left, 1 over x is going to be approaching negative infinity. These numbers are going to be very large negative numbers. Just try that on your calculator. Look at 1 divided by negative 0.00001. Evaluate that on your calculator. That's a very, very large negative number. So the values inside the parentheses in the sine function as x is approaching 0 from the right, these are approaching negative infinity. So basically you're taking all the oscillations out here and smashing them down towards the origin on the other side. And that's why you get the infinite number of oscillations occurring near the origin for this function. So that's what's going on. Alright, so that concludes this discussion on when limits do not exist. And for some of the examples that we've looked at, we will discuss them in more detail, such as when the limits are when we have vertical asymptotes. We will be discussing those in more detail later on.